is to study an old problem in nonlinear PDE, namely the stability of traveling waves, now also under the subject of noise. Before I do so, I would like to formulate or explain to you a little bit about the motivation of the background, why I'm studying this equation, particularly this one. And for this, I will use, let's say, one half of the talk to explain a little bit about the background of the Nagumo equation and the phenomena I'm studying, because it comes from the Nagumo system modeling the pulse propagation along the axon of a neuron, and this is what I'm ultimately interested in. Okay, I would like to introduce shortly some vocabulary, because I don't think that you are familiar with this. So neuroscience is study of the nervous system, and the basic or central object, among other things, is the neuron, a single neuron. And here's a, let's say, caricature of a neuron. So we have the soma, or the cell of the neuron. The neuron receives some input from neighboring neurons, and from time to time it sends out a signal along this axon to the terminal axon, and these are connected to other neurons that receive the signal from this one. So always the motion is from the left to the right, and well, it is a very celebrated result by Hodgkin and Huxley in 1952, who gave the first, let's say, mathematical description of the action potential, or let's say the propagation of the action potential along the axon. And still, although this is an old model, it is still the principal dynamical model for, let's say, the spiking behavior of the neurons. Right, yes, exactly. Okay, so still the Hodgkin-Huxley system is four-dimensional, and it's difficult to understand the dynamical features of the system. And quite soon after the Hodgkin-Huxley model came out, there was a, let's say, mathematical simplified version which could explain, let's say, the basic feature of the phenomenon catched by the Hodgkin-Huxley model, and this is called the Nagumo model. And I'm studying here, or I would like to explain you or introduce now the so-called spatially extended Nagumo equations, which means that we, let's say, extend the neuron spatially, and would like to also study or incorporate the geometry of the axon itself on the, or its impact on the signal propagation. So in terms of the mathematical equation, it consists of two equations. The first one should in some sense describe the voltage, or describes actually the voltage variable. So this is also physical, but as a simplification, they only need a second variable, which is in this context called the recovery variable. And if you want to think of this as a slow-fast system, then that means that the voltage is the fast variable, and the recovery variable is the slow. The recovery variable is in some sense the collection of the dynamics of the ion channels governing the action potential in the Hodgkin-Huxley model. Okay, for, let's say, academic reasons, I would like to study this equation on this bounded interval, but later on also on the unbounded space, with respect to this control parameter I. The I is sometimes, or you could think of it as the input current driving the voltage. And well, under the, let's say, parameters which I fix in the following, we will have, in principle, the following dynamical feature of the system. So if we reduce for the moment the neuron to 1 point, and just consider the only the associated ODE system, then you can, let's say, distinguish three different regimes depending on the size or the height of the input current. Basically, if below some threshold I minus, we have some let's say sub-oscillatory behavior, or in some sense excitable behavior, which means that a typical, let's say, trajectory in the VW phase space looks like this. So here we have the null clients of the voltage and the recovery variable. So this is the intersection, so the critical point of the dynamical system. And in the excitable region, A typical trajectory in the VW phase space makes at most one large excursion and then comes to rest at this stable fixed point. So this intersection of this critical point actually is a stable fixed point in this case. If we increase the input current beyond this lower sub-threshold value, I minus, then we come to the picture in the middle, and the typical behavior now changes from one large excursion to some oscillating behavior around this limit circle, which is here indicated with this red line around the intersection of the zero null clients. And well, this is in some sense corresponding to the periodic spiking of the neuron. And if you further increase the input current, you can imagine, so you apply too much current to the neuron, then basically the neuron is destroyed, and actually what you observe is at most one excursion in the VW space, and then let's say the system or the dynamic system comes at rest at this super threshold value, which is again stable. So this one, so the one on the right hand side, the super threshold regime is for some reason, at least from the biophysical background, unreasonable. So I'm concentrating on the first two, the sub-oscillatory, respectively the excitable and the periodic oscillations. Okay, I just, in order to explain you the basic idea which I will apply later on to the Nagumo equation, tell you about what can be said in the oscillatory regime. So in this regime where the dynamical system exhibits some oscillating behavior here around this intersection of the null clients. Well, if you look at the corresponding dynamical system denoted by x of t, we would like to study, in some sense, the pathwise stability of this dynamical system. And if we denote with x hat the limit cycle, and capital T is period, then it's well known that if we look at this Lyapunov exponent, in some sense, so we look at the normal direction of the flow along the limit cycle. X hat is the limit cycle at time t, and we subtract in some sense the tangential direction along the limit cycle. So we control in some sense the normal contraction around the oscillating limit cycle. Then if this average around the periodic cycle is negative, implies exponential stability with a certain exponential exponent, which is related to this integral. So in some sense, this quantity controls the contraction, the average contraction around the limit cycle. And well, if we, let's say, or we can use this quantity to set up a direct pathwise stability result. The only thing which you have to take care of here is that if, of course, you have two different limit cycles with a different phase, they never come close. So what you have to take care of is that a given solution adapts to the right phase. And adapting to the right phase is accomplished by this, let's say, time change, which in some sense shifts the given solution to the given, let's say, periodic solution with the right phase. Okay. Exactly this kind of argument I would like, because this gives you some kind of pathwise stability result, because this has this pathwise result, can be carried over now to the stochastic case. And here's a toy example for the two-dimensional system. So if you had now Brownian motion, and for simplicity, let's assume we have a dispersion matrix, which is, or whose standard deviation in some sense is proportionate to the distance of the given solution to the limit cycle, then the same condition, so the negativity of the average Lyapunov exponent integrated around the limit cycle, gives you in some sense the same result as in the deterministic case. So if you specify a delta neighborhood sufficiently small, you can estimate the probability that the given solution of this SDE does not exit this delta neighborhood of the limit cycle, with this probability estimated on the right hand side in terms of, let's say, the initial distance of the given solution to the limit cycle. And well, that means if you again adapt the given solution to the right phase, it will be, let's say, contracting to the limit cycle. So this is, of course, a pathwise stability result, and due to the fact that we have chosen the dispersion matrix in such a particular way. Okay. So this is the, let's say, geometric picture I have in mind, and which I would like to, let's say, carry over now to the spatially extended model. So going back to the spatially extended case, first of all, the Nagumo model. So the basic feature of the spatially extended case I am interested in is that if I take the input current in the excitable region, I get, or the system allows for a transient pulse traveling along the x-axis, and here is a typical shape of this action potential. By the way, the parameters which I use throughout all these numerical illustrations will be kept fixed throughout all the dimensions also. And from the mathematical point of view, this is a simple, in some sense, a simple system to solve. So I use the following, let's say, modeling as an evolution system. So we consider the voltage and the recovery variable as L2 functions. And then we can realize this as a semi-linear system where the matrix linear operator A is this nice operator, and F is in some sense also nice. So in the sense of the basic mathematical facts are the matrix generates a strongly continuous semigroup, and the nonlinear term, the reaction term, is one-sided Lipschitz. So this is a typical feature of all these systems that model these neural models, because they come from, let's say, these nonlinearities in some sense model the reaction terms of underlying chemical reactions, of course, which are stable. Well, and using this, let's say, formulation, you can study, or the right approach to study existence and uniqueness is with respect to this standard Gelfand triple, and this is, of course, well known. So I would like to add now noise to the system in order to study various phenomena which come up in the real world study of neural systems, in particular various, let's say, subthreshold phenomena and other phenomena. I will explain one in more detail later on. And the sources of the different noises in these models are threefold. I won't get to explain it too much, but in some sense what I'm sticking today to is only on thermal noise, basically. So in the sense that I'm adding now a cylindrical Wiener process, later on also with multiplicative or with non-constant or state-dependent dispersion matrix to the given system. And I would like to think of this noise term using this, let's say, straightforward, let's say, Fourier expansion with respect to a given orthonormal system of the underlying L2 space. So a quantity which plays a role, of course, in this business is the spatial correlation, which is formally written up by this infinite series, and I denote the corresponding correlation kernel by QXY. Well, one motivation to study this equation, and later on the stability of the pulse solution, and later on also the wave in the scalar valued analogon of the Nagumo system, is the so-called propagation failure. So it is observed in real data that the propagation of the pulse is sometimes disrupted. This is attributed, for example, to exterior random sources, like, for example, thermal noise could be one reason for that. Here's a typical, let's say, numerical illustration of that. So if sigma is small, the standard deviation, we see that the action potential in some sense propagates from the right to the left in this picture. But if we increase the noise intensity on the right hand side, we see that at some point the action potential somehow fails to propagate anymore. There are various numerical studies about this. In a series of papers, in particular on the spatially extended Nagumo paper by Tuckwell in the years 2008, 2010, and 2011. So a typical picture which they, let's say, derived on the probability of faithful transition. So I should stress this in this point. Now he's considering, let's say, the probability that the action potential is actually propagated and not fail to propagate. So it's the, let's say, complementary probability, of course. So here's a typical picture you can guess of. So if you increase here the intensity of the noise intensity from 0 up to, let's say, 0 to 7, a typical picture on the probability of faithful transition or transmission of the action potential of the signal, if you want so, is looks like this one. So the second curve with the diamonds is a curve you get if you restrict the noise, for example, to this spatial area in this, let's say, setting around 2.5 up to 3.5. As I first saw this picture, so this is done by, in some sense, visual inspection. This reminded me very much of exit probabilities of One-Chan-Uhlenbeck process. And what I give you now is the, let's say, mathematical justification of this curve. The computational approach, I call it, is as follows. So first of all, you should come up with the right estimator to estimate this propagation failure probability. I tried various estimators, and it turned out that the simplest one was exactly the right one. So it is exactly the average area of the voltage above of the resting potential. So V star should denote the resting potential, the value of the voltage when the neuron is at rest, so that at most of the area V minus V star is positive. It can be in the recovery phase also negative, but that doesn't play a role, because what I observed, or what you can observe in the simulations, is that the distribution of this functional has a distinct bimodal distribution. And with respect to this, let's say, estimator, you define the failure of the propagation of the action potential just with respect to a given threshold, because you observe this, let's say, bistable bimodal distribution. You can fix well threshold between this and say, okay, propagation failure occurs if for some point t this integral falls below this threshold, because then in some sense the action potential vanished basically. I need some initial time. This is for technical reasons, or if you want so, the system needs some time to adapt to the faithful transition. Okay, so that means we are interested in calculating basically this probability that the infimum of this estimator falls below this given threshold for some instant of time between t0 and t, the terminal time, let's say. Well, the ansatz to calculate this probability is now this is the reason why I'm interested in the stability. Well, once if you believe in the exponential stability of the traveling pulse solution, then you can just linearize the given SPDE around this traveling wave. So as I did it here with some given rate, which you can actually calculate or estimate. You can also give variational characterizations of that, plus some, let's say, for simplicity, Wiener process, which has some standard deviation, which is constant. If you apply now this approximation, this crude linear approximation to this estimator which I've just introduced, which is linear as well, linear, then you end up with, let's say, a very easy one-dimensional stochastic differential equation, which we all know. This is a one-dimensional One-Chan-Uhlenbeck process. And the only parameters you have to calculate here is the sigma tilde, which can be, let's say, estimated from the model. Also, the capital C, which is basically given. It is just the integral of one pulse you observe shifting around or traveling around the axon, and then also this quantity capital star. And once you have done this reduction, your initial problem of estimating the probability of faithful transition or propagation failure, the complementary probabilities, just reduce it to this first passage time probabilities, of one-dimensional Ornstein-Uhlenbeck processes. And it is really remarkable good, this linear approximation, because, for example, this is a simple, let's say, plot you can get. So the blue one is actually the red one is the Fitzhugh-Nagumo system. The blue one is the Ornstein-Uhlenbeck approximation. And so this is now the probability failure probability. So it goes the other way around, not the probability of faithful transition, which would be the complementary. And you see that it exactly fits. It also fits with the observed data reported in the paper by Tuckwell. Okay, you have seen that in some sense the most important assumption here in this reduction is the linearization, so the exponential stability. And this is now, I now come to the, okay, this is another slide which shows you, because I'm talking to scientists, neuroscientists about this. So what they did not take into account or cannot take into account with their, let's say, models so far is, of course, let's say the spatial correlation structure of the noise, because they simply don't have the models for this. But you can imagine that once you have set up this general associated evolution system with a general function valued Wiener process, you can study also now the dependence of the propagation failure probability on the spatial correlation as well. And it is clear that in some sense the smoothness of the correlation operator should have some impact on the probability failure. Okay, this is one illustration about that. So also, okay, this is an outlook on 2D systems. Instead of looking at one traveling pulse, you can look at neural ensembles. And let's say the analog of the pulse solution are, let's say, various spatial structures which reflect some kind of synchronization in neural ensembles. Here's, for example, a ring that in some sense grows up to the boundary, and because I've chosen here the Neumann boundary conditions as well, so in some sense at some ultimate time the ring here somehow vanishes. And of course you would like to see how is the impact of the noise on this expansion. Here's another one where you can choose various, let's say, configurations, how they move around in the space. Okay, now I come to the mathematical part. The mathematical part now, let's say, I would like to set up a theorem that strictly proves stability of the analog of the traveling pulse solution, because I don't have yet a result for the Fitzhugh-Nagumo system. And to ease, in some sense, my life, I will reduce now to the scalar valued case. And this is the case where I'm setting in the Fitzhugh-Nagumo system the recovery variable to a constant value, so epsilon is set to 0 and equal to the input current in the excitable region. So what you end up then is a persistent pulse. And what is a persistent pulse? A persistent pulse is nothing else but a wave, right? Okay, and this is the exact analog I'm interested in. So the wave, or the stability of the wave in the scalar Nagumo equation in the excitable region. So this is this equation. And in that case, in the deterministic case, you can explicitly calculate actually these wave solutions. So this is why this is so, let's say, left example. So the shape of the traveling wave looks like this. And you can also calculate the speed at which it travels from the right to the left under my parameter setting. Here's a typical illustration on the traveling wave front subject to noise. Again, no spatial correlation, so IIDs, Wiener processes sitting on the grid points of the space domain. So you see these little fluctuations here depending on, of course, the noise intensity. And this is a typical space-time plot, so time is running from downwards. You see that after some initial period, which depends on the, let's say, transient region where the wave or where the shape or the profile of the solution adapts to the exact traveling wavefront, then moves with constant speed to the left. And in some sense, this was my starting point. I wanted to, let's say, give a precise theorem for this picture. Okay. before I will step a little bit back to the deterministic case, because I want to, let's say, show you a new, in my sense, new method to prove the stability. So I'm a little bit, let's say, generalizing the coefficients, but this is not really important. So in particular, you can, let's say, formulate the wave speed in terms of these new coefficients here explicitly. Now, the first thing I would like to study is to find the right function space. Of course, there is a long history around choosing wrong function spaces in this area, but okay. One important thing also is I will study this equation on the whole line, because I want to, let's say, be away from the danger of using, in some sense, spectral properties of the Neumann-Laplacian unbounded domains, because there's a lot of, let's say, literature around saying, well, if we increase the diffusive coupling in the system pretty much, then we get stability, which is, of course, clear, but it kills the traveling wave solution. So it is a physically or biophysically unreasonable assumption. So you really need to stick to the parameters chosen here. And I've chosen the unbounded domain by purpose to be, let's say, not in the danger of using any spectral gap of the Laplacian, which is, of course, not here. Okay. Next technical difficulty is that the traveling wave is, of course, not an L2 function with respect to the whole line. That, of course, could kill you, but what saves you is that if you look at the different two-phase shifted traveling wave, then this is again in L2, and also the derivatives are L2 integrable. So that's fine. So we can study the stability problem in the L2 space, because we are only interested in the difference to a given traveling wave. The ansatz to look at the stability is, let's say, pretty standard. So we could decompose the given solution V with respect to a given traveling wave and call the difference U. And the resulting equation for U looks like this. And this is now a nice equation in the sense that we can model this in the variational framework with respect to this almost the same Gayfund triple as before. So this is also standard. Now, to prove the stability of the equation, well, the basic strategy you would like to use, of course, is to differentiate, for example, the L2 norm. And if you do this, then at least for, let's say, a given solution sufficiently small to the traveling wave, and you would like to, let's say, show this exponential decay with kappa star, with rate kappa star, at least for Vt sufficiently close. If you formally differentiate this and integrate by part, the usual thing, you end up with the monotonicity properties of the reaction term here, and of course you know that this reaction term is bistable, so it is not monotone. So as you might guess, it is of course not strictly dissipative in that sense. We have heard in the talk by Professor D'Aprato in the morning, so only quasi, let's say, dissipative, and that of course kills the contraction. It is, of course, clear that it cannot be contracting, because if you look at the difference of two wave solutions, they never come close, because they are just moving with the same constant speed from the right to the left, or from the left to the right, depending on the parameter region you have chosen. And so that means that the L2 flow cannot be contracting in any direction. It can be only direct contracting in certain directions. And if you now go back to the introductory example of the oscillating Fitz-Nagumo system, you know what is the contracting direction and what is the non-contracting direction. So you need to, let's say, differentiate or distinguish, between tangential and normal directions. So this is problem one. So you need to try sorting out the contracting directions. And, well, this is done by the usual, let's say, linearization of this nonlinear term. I forgot, by the way, the Laplacian here, which gives rise to this integral with minus u here, plus some remainder term which is controllable. And let's say the basic, let's say, inequality, which gives you then later on the local stability, is that if your profile U is orthogonal to the gradient of the traveling wave, so the infinitesimal direction of the limit cycle in some sense, then you have this kind of, let's say, Poincaré type inequality. And for the linearized system, which you linearize around the given traveling wave. And the geometric or the connection, or to prove this, is I think very nice, because it now gives a link to Schrödinger operators and ground state transforms, as you will see in a minute. So this is now explicit calculation, where I show you later on a result that this is true for general bistable reaction diffusion systems. Well, in this case, you know the traveling wave explicitly, then also the derivative, so the infinitesimal direction of the flow. And if you linearize, if you apply or plug in the derivative into the equation satisfied by the traveling wave solution, you realize that it is a solution to this eigenvalue equation for the Schrödinger operator with this potential. And then there is a standard machinery and Schrödinger operators to represent the spectral properties of the Schrödinger operator with a given ground state using, so this is place a row of the ground state, by using the ground state transform. So you change, in some sense, the coordinates. So you write your given U with respect to the given ground state with respect to times some density H. And in terms of the density H, the quadratic form you would like to control its spectral properties can be rewritten like this one. And once you have investigated the shape of the traveling wave, it has some exponential decay. Also, this is typical for bistable reaction diffusion systems. You realize immediately that the corresponding quadratic form given or induced by this ground state transform, or so-called ground state transform, has a spectral gap, which can be explicitly calculated, by the way. So plugging this together into the initial, let's say, linearized Schrödinger operator, you end up with the desired estimate, which I would, or mentioned at the very beginning. Well, this was one of the problems. I'm just, let's say, mention in a minute that this is true for general bistable systems. But another problem is, of course, sorting out the right phase of the given solution. So if you compare your given solution with the wrong phase or wrong phase shifted traveling wave, then you won't be able to prove exponential convergence or stability. And there is a simple idea which I already also briefly discussed at the introductory example in the case of the oscillating Fitzhugh-Nagumo system, that you can apply exactly in the same way here to this Nagumo equation. So you just shift the given traveling wave by some speed c of t, where c of t is now the solution of this equation, which in some sense shifts the given traveling wave towards the given solution v of t. And once you do this, and well, what is this kind of gradient? So this is some kind of gradient dynamics with respect to a given certain relaxation rate, which you can choose later on, sufficiently large to get your desired, let's say, convergence rate. Well, this should remind you of this kind of gradient dynamics. So if Vt would be constant, so this given solution would be independent of time, then this would be just the dynamics that minimizes the L2 distance of the given profile V to the orbit of the phase-shifted traveling waves. So that means that this dynamics with this C of t given as the solution of this equation converges to the critical points of this function. Okay, and the nice thing is that you can plug in anything together to get a pathwise stability result that then, and this was the ultimate goal of the business, can be carried over to the stochastic case as well. So well, you get now with this phase-shifted traveling wave exactly the kind of exponential decay you would like to get with a straightforward differential of the L2 norm, at least if you are pretty close to the given solution, to the orbit of the traveling wave. Okay, you can plug this in together. All estimates are explicit here, and also the kappa star actually are explicit, and also the C star. I've just, let's say, used this for simplicity to ease the, let's say, presentation here, and you get this kind of result. Okay, once you have this, you can, okay, so this is just one detour to the general bistable case. You can replace the polynomial, which is a particular polynomial in the Nagumo case, by any bistable reaction term that has 3 zeros. 2, 0, and 1 are stable, and A is unstable. And F should be negative on the first interval from 0 up to A, and positive from the second interval from A up to N. Under this assumption, you can prove that there exists a traveling. So this is well known that this exists a traveling wave solution, and the gradient solves exactly the same equation as before. And now the new ingredient, in some sense, if you want so, is that if the reaction term is convex on the first part of the interval from 0 up to, let's say, some point x naught, and concave on the second half of the interval, then the potential you add to the ground state of the Schrödinger operator is unimodal. This is the point. And it typically looks like this. So it has one maximum, which is above 0. This is the black line. It is because of the assumptions on the stability of the reaction term at 0 and at 1 approaching a finite negative value, both at minus infinity and plus infinity. That explains the exponential decay of the ground state. And the ground state typically looks like this. So this region where, so it will be convex at infinity with the given rate, which is exponentially, can be calculated from the derivatives of the reaction term. And it will be concave here in this area. So it's a simple analysis, and then if you are familiar with functional inequalities, this information is enough to explicitly calculate everything you want to have. And everything is explicit in terms of the reaction term. Okay, I can use now or I can add this, or I can use this pathwise stability analysis now in order to add a noise term, exactly in the same, for simplicity, in the same kind as before in the simple Fitzhugh-Nagumo system in the oscillating regime. So the noise is again modeled by some dispersion coefficient that whose standard deviation is proportional from the distance or to the distance of the given solution to the orbit of the traveling wave. So these are in some sense, awkward formulated assumptions because in some sense you are not in L2, so you have to be a little bit more careful in the precise formulation of the result. And using exactly the same kind of arguments that I have, let's say, used to produce the pathwise stability result for the oscillating Fitzhugh-Nagumo oscillator with noise, subject to noise, you can also prove that now for the solution of the phase-shifted Nagumo equation with this noise term, you can specify a small neighborhood such that with high probability the given solution does not leave, or you can estimate at least the probability that the given solution does not exit the orbit of this generated by traveling waves explicitly in terms of the initial condition, and on the set where this is infinite, this exit time, the solution actually converges pathwise to the traveling wave solution. Okay. One last slide, one last slide concerning the danger of setting up models which should try to analyze or model the impact of noise on stability properties. So here's one example that I would like to present, and also presenting to people from neuroscience. So you can, there's a lot of literature around saying noise or the impact of noise can have stabilizing effects on dynamical systems, which is of course true, but which is also not true in some sense. And this is an example where you can see that it is in some sense sometimes unreasonable. So here I have considered the same equation with a given, let's say, state-independent noise, additive noise term, which is in some sense arbitrary, and I couple this with one given Brownian motion. Okay, so this is the new term here. So the function, the profile V, is coupled to one stochastic process, one scalar value Brownian motion. And well, if you now study the, let's say, stability properties of these SPDE, then you can see, well, if I consider two solutions with respect to two initial conditions, you can end up with this, or you can estimate the distance with respect to the L2 norm by this exponential martingale times the L2 distance of the initial conditions. So here's the beta t showing up. And you can see if you turn on the noise large enough, then you can make this exponential rate negative. And of course, this exponential rate kills the growth of the Brownian motion, because the Brownian motion is growing sublinear, which means that if you increase the noise strong enough, then this system is exponential stable. But the original information of the system is totally lost. What you observe in the end is only the statistical information observed with this additive noise. So this is, let's say, an example that shows that if you do this in the wrong way, adding noise and studying the stability properties, then you can end up with, let's say, an empty result and with nothing. So thank you very much. So, yeah.
Very much. Questions or comments?
Psi?
Sorry?
What was the strength of this
Psi is a Q-Wiener process. So for simplicity, Q means a trace class operator. So that you can model
trace
this.
class in R2.
Yeah, that has nothing to do with trace class. It is only because of the additivity of the noise.
No, but I mean, these equations have of course been investigated in this context of phase transitions, right? And
Yes.
And of course, they are the non-L2 psi has been looked at, and then of course you have a completely different behavior. Then somehow at infinity, the large deviations will kill the traveling wave behavior.
Yes, but this is not the point. The effect that kills the traveling wave here as well is the coupling of all spatial components to one Brownian motion. This is the point. So this is in some sense a different phenomena, which you could also, you would have, if you take L2, if it would take space-time white noise, you would have superposition of these both killing, let's say, phenomena.
Well, about your problem on the whole line. If the function f is, however, monotone, you can avoid this space L2. You can work directly in L1 and prove that the problem is well posed. But I don't know if you have significant situation, f is monotone.
Yeah, I need the geometry of the Hilbert space for my analysis.
No. In deterministic case. In deterministic case, you can work in the L1. Is well posed.
Sure. You can also, the classical, this is an old story in PDE. Usually the people consider it bounded PV function.
No, I mean PDE. In fact, PDE in L1 is well posed. It's a function f nonlinear.
Yeah, I don't doubt it. Yes.
Okay.
Right. Oh, sorry.
Well, I was just going to ask. You mentioned also like one question that you might think to generalize, where you're talking about the strength of the noise with the correlation of the in space of
Right.
of the space time. What did you find it?
But you can also
Like, how did you study the?
well, if you look at the okay, so the smoothness of the noise has an impact on the of the propagation failure probability. So the smoother the noise, the more or the higher the higher the spatial correlation. Let's say it this way. The more non-local the input of one, let's say, stochastic forcing term at one point of the phase space is on the whole profile. So that means that the higher the spatial correlation, the lower the probability of phase failure transition. So the higher the failure probability will be. And you can quantify this with this model. So this is the observation. And if you look at the, let's say, typical numerical illustration of these functional Wiener processes, you see why. Because if you take a Wiener process with the same standard deviation, but you change somehow the spatial correlation, you see that if the spatial correlation increases, the maximum of the sheet will also increase, and this will have some impact on the stability properties. It's not in general true, but if you choose in this setting, I usually choose the spectral, let's say, approximation of these Wiener processes. So with respect to the Neumann equation, and then you see this.
So, thank you very much. Okay.